Imagine a world where base metals could be smelted without any carbon. Welcome to today's webinar. My name is Tara Ryan, a member of the pyrometallurgy team here at Glencore Technology. Glencore Technology is a technology solutions provider, operating for over 40 years and servicing the minerals and mining areas. We've installed our technology in all continents and have long-term relationships with our 2,000 plus customers and suppliers. Today's webinar is titled Towards Net Zero Pyrometallurgical Processing with ISASMELT and ISACycle, and it's a discussion in continuation from our recent paper and presentation at the 2023 Advancements in Pyrometallurgy, Smelting in San Diego, California. In today's webinar, we'll begin by exploring the role of base metal smelting in the path to zero carbon. Then we'll hear from Dr. Stuart Nicol, who will explore the zero carbon potential of ISASMELT technology. Finally, we'll open the floor to an audience Q&A. So firstly, the importance of zero carbon base metal smelting. For many organisations, the path to net zero involves investing in a transition to zero carbon through renewable energy and energy storage. And with metals like nickel in electric vehicles and copper in solar panels for renewable energy, metals demand is expected to soar. Between now and 2040, for example, copper is projected to increase by 45%, lead by 40%, and zinc by 30%. And with the mining industry's carbon footprint currently contributing to 7% of global greenhouse gas emissions, we must evaluate how these high metal demands are currently being produced. So given this context, metal producers are in prime position to seize the opportunity to not only optimise production for these growing metal demands, but also to decarbonise their operations. And by doing so, can ensure the provision of zero carbon base metal products, also known as green metals. The awareness of this opportunity is growing across the industry. A recent mining sentiment survey by White & Case asked a range of mining leaders what they viewed to be as the most critical structural change they expected due to increased environmental social governance focus. 46% of respondents said the shift to reducing carbon footprint, and 38% emphasised that underpinning enabler, which is green metals production. So, and also to further embody this opportunity, lots of companies as well are driving progress through setting targets and incentives for decarbonisation. So within the mining value chain, smelting operations play a key role in the production of discussed metals in demand. Decarbonisation of smelting processes is therefore crucial. A breakdown across commodities reveals steel and aluminium as leading contributors to the industry's CO2 emissions. And until now, most investments and discussions surrounding heavy industry decarbonisation have focused on these commodities. However, base metals still produce a large volume of emissions. In 2020, they produced approximately 53 million tonnes of carbon dioxide equivalent as a collaborative across all base metal commodities. And as mentioned, with forecast projecting production of these metals to increase by 30 to 45%, these emissions will continue to grow in significance. Base metal smelting solutions are therefore key to the green metals transition and for green metals production, to prevent 1 billion tonnes of global carbon dioxide being emitted over the next 20 years. So then, what solutions are there for base metal smelting, and are there low-cost solutions? Dr. Stuart Nicol will now present how this can be achieved with ISASMELT technology. And just a reminder to please submit any questions for the Q&A portion within the chat, and we'll get to as many as we can shortly. Thank you.
So a bit about myself. So I'm Stuart Nicol, as you can see. I'm currently a senior metallurgist in the pyrometallurgy group. So I've got both a bachelor and a PhD in extractive metallurgy from the University of Queensland. And I've worked in a wide variety of roles and places around the world in the base metals industry. So I've done a lot of research and development, operational experience, design, projects, and a lot of other sorts of work in the base metals industry. And most commodities, copper, lead, zinc, nickel, tin, iron, most metals out there. So how does ISASMELT approach low carbon? So we've been doing low carbon smelting for a long time. So the ISASMELT furnace was developed to reduce costs primarily. So Mount Isa Mines had a smelter in North Queensland, and they'll bring a lot of coal from central Queensland to site to smelt. This was the largest cost for them while running. And so the technology was developed in order to make the site more profitable. It was a high cost site, and they wanted to get as low cost as possible. And so they went out there, investigated technologies, new things that they could do to bring their operating costs down. So they stumbled across the Smelt technology at SARO, and they took that and developed it and did a lot of research and development to bring it up to what could be implemented in industrial processes. So they installed their first ISASMELT in 1992 at the site, and by installing the technology, they reduced the coal and became one of the lowest cost, well, the lowest cost smelter in the region. And so what sort of results did they get? So it was primarily aimed at reducing costs, coal costs. And so they had a 92% reduction in the coal used in the smelting process. So when we look at CO2 emissions, this means that they had a 92% reduction in the CO2 emitted from their primary smelting furnace. It's a huge reduction. And if we look there, that's pretty close to 100%. There's not a huge gap there left. And this particular change, where the furnaces are installed to reduce operating costs, is quite common. Most ISASMELT plants, if not all of them, are the lowest cost smelter in the region which they're installed, and they use very, very low amounts of fuel. A good example of this is the southern Peru site. So they did something similar. So they installed an ISASMELT furnace in order to reduce the costs for their smelting plant to become low cost. They're currently one of the lowest cost, if not the lowest cost smelter in their region as well. And they were using old technology with lots of fuels, just like Mount Isa. So they installed the ISASMELT technology to reduce the fuel costs to become more profitable, but in the process, they saved a lot of carbon. So you can see here for them, Mount Isa mines, the particular measure we used there was on the primary furnace. For southern Peru, this was the entire smelter, and they saw over a 65% reduction in the fuel used from the smelting process, which results in a greater than 65% reduction in CO2. So you can see here that although a lot of these smelters and projects which we worked on were not developed or weren't done for CO2 savings, they were done primarily for cost savings, capital savings, and efficiencies of the smelting process. But by being so efficient in how they run, they've used very little fuels, and we've seen huge CO2 savings. So the question is we have our technology, we've been doing it for a while. We're not quite there yet, so what does the future hold, and how do we get to net zero? So if we look at what we need to do, people are targeting 2050 for net zero processing. So if we look at how we did what we did, it took about 15 years to go from the SARO tests to the first installation in Mount Isa, and even now we're still being accepted and deployed in industry. We're not the dominant furnace technology yet. It'll take us another few years before we are the dominant technology. So if you look at the path taken for us, this is not short. If we look at how long it is to 2050, this is not long away. We have to develop technology, install it, implement it, develop it, and then roll it out across the industry. Huge numbers of smelters, huge numbers of facilities required. It's not likely going to be new technology from the timeframes, from what we've seen. It's most likely going to be the development and advancement of existing technologies. So you can see that for us, we can see the ISASMELT technology is already extremely energy efficient and CO2 efficient. And so we can see as small changes and small developments in our technology will get us to net zero in time for 2050 and can be adapted and installed on our existing ISASMELT plants. So this particular presentation will sort of explore why we are so CO2 efficient with our current technology, and then what we see needs to happen to close that last little gap. So the topics we'll cover is, so we'll briefly describe the ISASMELT technology and how it works. I'll go through the traditional and emissions reduction optimization techniques which have been used in industry. So the traditional is all about that costs and profitability which we've been traditionally chasing in the smelting industry. Emissions reduction is more about what we'll be seeing when we want to reduce the CO2 emitted from our smelters. We'll then sort of cover how we've optimized this ISASMELT process historically and what we need to do in the future. And then most importantly, some of the maintenance required and a bit of a summary. So first, how does the ISASMELT furnace technology work? So that there is a bit of a schematic of our furnace. You can see it's a tall cylindrical vessel with a lance in the middle. So you can see it's a simple steel shell. There's no advanced water cooling elements, just simple refractory brick. It's a tall vessel with just that central lance. We have feed that falls in through the feed chute at the top. We use a simple conveyor belt system, and it falls into the molten bath where it reacts. So that feed system, simple belts, you can go out and shovel it, you can reverse the belts, change things out, so it makes it very simple and reliable. The feed preparation system is just a simple agglomerator, so something like a paddle mixer or a drum mixer, something very simple to sort of agglomerate and get things going. So that feed falls into the bath where it reacts. We inject gases down the lance, so that's air all the way through to industrial oxygen, so 21 through to about 92+% oxygen through the lance. So this is where things happen. So that oxygen goes into the slag and dissolves, and that then gets carried through to the feed materials. So that slag acts as the oxygen carrier in our smelting process. So that gases goes down, reacts with the stuff that falls down in the feed chute, or the feed materials in the bath, and then reactions occur. This then generates our molten products, so slag and matte or metals, as well as an off gas. Now, as you can tell, that lance sits inside the bath, and that's a simple steel pipe. So this is a key aspect of the technology. So we use specialist internal designs to get gas flowing down the lance in the correct way to cool down that steel pipe. So that pipe is cooled by that air, so it means that when slag contacts it, it freezes on it, forms a freeze lining. And this freeze lining protects the lance from the aggressive conditions in the furnace and means we can submerge that steel pipe into the molten bath. So we can get 10+ days of continuous operation of a single lance without changing it out, with the record currently being about 40 days. The gas is generated from the smelting process, extracted through the top of the furnace through a port. It then goes through gas cooling and dust collection to collect all those materials. So various technologies available there: waste heat boiler, spray coolers, hot gas ducts. You've got bag houses, ESPs, and other sorts of gas collection equipment, things like scrubbers as well. The other thing is our molten products. So they're either batch tapped or continuously extracted from the furnace through tap holes or through overflow or underflow weirs. Generally, we prefer the tapping systems because they're more robust and reliable and easier to maintain. And so you can see there's a photo of an operator there tapping our furnace. And so we generally batch tap, and while we're tapping, we've got a lot of measurement and controls. We've got online measurement of temperature, gas conditions, and we do some checks while we tap as well, so chemistry as well as some spot checks of temperature. And then lastly, we have got our control room operator, and he continuously monitors and controls that plant as we run. So, taking a step to greenhouse gas emissions and now how they occur in the smelting. So I've sort of given a bit of an understanding how the ISASMELT furnace works. So now we sort of need to explore how we emit CO2 in the process. So there's 3 scopes of emissions. So scope 1 is all the stuff we can control as metallurgists designing our plant. So this is all the feed materials and reagents and reactants and things we're putting into our furnace that goes into the plant. And then of course we have the stuff coming out. So all those chemical things we can mix together and make it. We then have scope 2. So this is all the energy required in the smelting process that gets generated outside of the plant. So this is electrical power, so you run motors and things like that. Heating and cooling, so this is things like hot gases and things to keep things hot if you need it. And of course cooling as well, so chillers if you need it. So the bigger one for smelters is generally their electricity, and that's probably the scope 2. When we look at scope 3, this is also important. So this is all the things being transported in and out of the smelter, as well as the things that are being used to make a smelter. So that's scope 3. When we're looking at metallurgical processes and what we can do when we design our furnaces, the biggest impact we have is on scope 1. Everything else we can sort of push onto other people. So scope 2 and scope 3 we can push onto other parties to manage and control emissions, but we have to focus on scope 1. And so that's where a lot of the work and focus we are taking at the moment is centred on. And so a lot of the presentation we're talking about scope 1, but we'll also cover scope 3 when it comes to maintenance and consumables, because that's important when we're building and maintaining our ISASMELT technology. So that hopefully gives a brief understanding of the different scopes, which is commonly talked about when we talk about CO2 emissions. So what is carbon used for in smelting? So carbonaceous material is used in smelting for 2 reasons. The first one is heating and energy. So smelting processes need enough energy to get the materials to temperature to do what we need to do. And so carbon is a cheap, easy to use fuel source to provide the energy we need. The other one that we use it for is for reduction and reaction purposes. So those carbon materials can act as reductants, pulling oxygen out of materials. So it does some chemical work as well. So there's the 2 purposes there that we can use it for. Of the 2, heating and energy is probably the easier to replace because you can change the energy forms and what you can use for energy, changing from carbon to electricity and things like that. The more difficult one to replace is your reduction and your reactants, because there's some very specific chemical fundamental properties of carbon which are hard to replace with other materials. So now that we know how carbon is used, how do we get to net zero? So on a practical way, there's two steps. The first one is we want to reduce the amount of carbon we use as far as possible. So this means we use as little fuel and as little reductant as possible, getting the maximum efficiencies we can. So this means is we then need to replace as little as possible. So it means that that makes our job for the next one easier. So reduce and then replace. So replacing is where we change out the carbonaceous material with some alternative. And so when we're looking at our ISASMELT technology and how we're getting there, the first step, reduce, targeting high efficiency processes and smelting is the key, and we then want to swap it out. So we've been focusing on reducing for a very long time because this is a big driver for smelting operating costs. So by being traditionally cost-focused and cost-centric, a lot of sites have become quite efficient in how they use their materials. So there's a number of challenges with this though. So when we're looking at some of the properties of carbon, there are some fundamental chemistry limitations, what we can and can't do with other chemicals. So this makes it quite difficult. So things like carbonates in your feed. So if you've got calcium carbonate in your feed, you can't really remove CO2 because it's chemically bound within the feed materials. Similar things you might be able to get is if you've got concentrates with carbon in them, you can't take the carbon out of the con easily, and that'll always emit CO2. So there's some fundamental chemistry which we can't get away from. And another one, of course, is your operating flexibility and operability. So carbon, particularly in the form of coal, is very easy to handle, very easy to process and do things with. You know, a lump of coal is not likely to explode. You compare that to diesel or natural gas where it's more volatile, more reactive, you need more containment and more systems. A stockpile of coal is much safer, very easy to operate. You can go out there with the shovel and you can shovel it off. If you have a problem with the belt, you can simply reverse it and put it down on the ground. So it's very easy to run, very good operability, and as a result, that's why a lot of the smelting processes that we've worked with have used coal. And so when we move towards low coal options, this will have impacts on the operability and flexibility of our smelting processes. The last one, of course, is safety risks and project risks. So with any new technology, there's new things that happen, changes happen, and with any change there is risks. So when we're swapping out coal for other things, we just have to follow that due diligence process to make sure what we're doing is safe and works well. So you can see there that sort of gives us a few steps in how we get to net zero. So the next few slides will sort of talk about what we've done and then the gaps. So when we're looking at smelting, a lot of us have followed traditional optimization approaches. So this is all focused about profitability. So this is about making as much money as you can from what you've got. So we typically want to increase the revenue, so increase the amount of tons we're smelting. We want to increase the recovery to get the most out of the feed we've got, and of course have as low cost feed as possible. So that's on one side, getting the maximum value out of our feed. The other one is we want to have the lowest cost. So this is things like low fuel, low flux, low electricity, low labour requirements, low maintenance, and small numbers of parts and masses. So there's lots of things we can do here. So there's two ways we optimise for profits. So the first of all is metallurgical approaches. So this is things like changing your furnace feed rate, changing your fluxes, changing your slag design. So things like the iron to silica ratio in your slag, you can adjust that to sort of optimise your profits. You can go for oxygen enrichment as well to sort of get more tons and things out there. You can change things like your mat grade and on what you're doing. So that's on the metallurgical side. So that's all the process chemistry. The other one, of course, is your mechanical equipment. So this is about getting as much as lower cost equipment and getting the longest life out of your equipment as possible. So this means that your furnaces are low cost, your parts are low cost, and they last a long time. So this is things like your refractory design of your furnace, the steel components you use, motors, controls, and systems like that. So we want to have parts that have got very long campaigns. So we're talking about smelting campaigns. 4 or 5 years is what we target, not 1 to 2. So this is what we've been focusing on for a long time. We have optimized as far a long way towards this. So this is what we traditionally do. When we look at emissions reduction optimization, you can see that there's not much more extra that needs to happen. You know, emissions reduction, it's mostly about changing out some fuels. So that's alternative fuels, swapping out your carbon for something else. And that's on top of the traditional metallurgical optimization. That's a small extra little thing there. On the maintenance and mechanical side, a lot of this is about capturing more energy from your system, so installing more equipment to capture more energy, to recover that from your process. and of course choosing materials which are lower footprints. So different grades of steel where you procure your steel from as well. So you can see that by chasing that traditional optimization approach for profitability and operability, you go a long way. And so that's what we found in the ISASMELT is the traditional approach, like what Mount Isa mine saw, got them a long way to zero carbon smelting. So what have we done? So if we look at the developments of ISASMELT technology to chase its efficiency, a lot of the things we've done have not really been targeted towards CO2 or fuel reduction. A lot of it has been targeted towards operability and performance of a smelting process. So one of the earliest developments was on feed agglomeration. So in a smelting process, some of your feed materials report to the dust. So portion always dust is what we call mechanical dust. So the challenge with dust is it goes into your furnace and then goes out of your furnace and then you have to put it back in again. So it's this recirculating load of material. So for some smelting processes, 10–20% of your feed materials can go to the dust. And that's a huge stream you then have to handle and rehandle. Dusts contain toxic elements, so it's a bit of a hazard the more dust you have. It's complex because it's all dry and the material handling is complex with screw conveyors and systems. And the other one is high dust streams make it hard to bleed your minor elements. So a lot of the volatile components such as arsenic and cadmium can get enriched in your dust stream. And that high tons dust stream with the low concentration of minor elements makes it more difficult to bleed them from the plant. So what they did is they developed feed agglomeration techniques. So what this did is it stopped those ultrafine materials in your feed from reporting to the dust. So this reduced it from over 10% to less than 1.5%. So you can see there that it's close to a tenth the size of what it was before. So it's low material recirculating load, so it makes it easier to handle, less work, less costs. But in addition, it also means by having a smaller stream, those complex elements are more concentrated in that stream. So they can more easily treat and bleed them from the plant. This is really important for things like arsenic in South America. But there is an energy saving here. So that dust, by going in and going out, gets heated up by the smelting furnace. And by reducing the amount of dust, you're reducing the amount of energy that's used just to heat up and cool down dust. So you can see there that you save about 5 megawatts on a 350 kTpa copper smelter, which is a huge energy saving. So that's one of the first ones. The next one along was probably oxygen enrichment. This is generally done in smelters for process intensification. So plants have gone from air to industrial oxygen in order to increase their throughput through a given furnace without having significant capital expenditure. So by going to a higher oxygen content in the Lance gas, it means that you can push more feed through while having the same off-gas volume. So roughly going from 21 to 92%, you might have 4 or 5 times, well, roughly 4 times the tonnage being able to be processed through the furnace without having significant capital expenditure. But you do have some oxygen enrichment there. So that is being done quite often on plants, particularly target high tonnages. Places like Tuticorin in India and MIM, they have chased oxygen enrichment to increase tonnage from the site, which increased profitability because you're getting more production from a given asset. The next one along that we've worked quite hard on is our furnace lining system. So if we look at the lining systems, the copper elements are quite expensive, and this is quite common in the base metals industry, but they cost a lot of money. So a good example of this is comparing Olympic Dam and Mount Isa mines. So they went through major furnace shutdowns last year in 2022. The Mount Isa mines one cost roughly $50 million to shut the plant down, rebuild it, reconstruct it, while Olympic Dam was about $500 million. So huge cost difference there. And if you look at the lining system differences, Mount Isa mines use fully bricked furnaces. Olympic Dam used copper elements, and they're also more complex furnaces. So we use those fully bricked linings, and we've always generally preferred them because they are a very simple, very low-cost lining system. Very simple to replace, very simple to change out, particularly on the high-intensity smelting vessels. So a small compact furnace makes it very cheap for the lining, which means our annualized rebrick cost is very low. The next one along is our slag temperature control. So this one was developed initially to extend campaigns. So continuous online temperature measurement means we've got very, very tight control of the furnace operating conditions. So a lot of the furnace bricks are destroyed or worn rapidly through the upset events and uncontrolled periods where you've got very high temperatures. And so by having the online temperature control, you reduce these events and you can run at lower temperatures, meaning the bricks last longer. So you can see here, we've had a lot of energy savings from these. So although oxygen enrichment was about process intensification, you can see you can get about 8 megawatts of energy saving in the furnace itself by going for oxygen enrichment. Same thing for having a brick furnace. You can save about 8 megawatts compared to some of these high intensity furnace or other furnaces with intense water cooling systems. Same thing for the slag temperature control. By running at more consistent temperatures at lower temperatures, you get about 2 megawatts. So you can see there we've saved a huge amount of energy by optimizing and working on our process for things other than energy and CO2. So that's a lot of energy there. And if we look at what we can do next, we've identified the next few things we can do. So the first one is alternative fuels. So this was that simple swapping out of carbon. So the number of fuels we've identified and tested and trialed. We have tested hydrogen in the lab before on the crucible scale, and we did that in the 90s, and that worked on the crucible scale. So we're looking at seeing if we can scale this one up. The next one along is pneumatic lance injection. So this has been implemented in lead and secondary smelting. So the pneumatic lance injection, this involves injecting dry feed down the lance into the centre of the bath. So the purpose here is to remove the moisture from the feed before it gets into the vessel. By removing the moisture, that water vaporizes and sucks a lot of energy out of the smelting process. So that dry feed, we're estimating will save about 8 megawatts of energy there. The other advantage of the pneumatic lance injection is we believe this will reduce the dusting rate of the furnace, further improving the energy efficiency. And that last one, of course, is our trim coolant. So this one's currently in development. So one of the key aspects of the ISASMELT furnace technology is our advanced online temperature control. So we're having continuous online temperature measurement, means we've got excellent performance and excellent control of the smelting process at all times. But this means we have 2 temperature control methods. So we've got a coarse control system. So that's things that are put on the conveyor belts that feed up into the furnace, things like recycle, reverts, and things that consume energy to smelt. So we adjust that as our coarse control, and that acts in the half-hour to hour sort of time frame before it hits the furnace. We've also got short-acting trim control. So this goes down the lance and acts instantly in the furnace. So this gives us instantaneous temperature control. So traditionally we've used fuels down the center of the lance, so things like natural gas, diesel, and other liquid fuels. If we're going to go to net zero, we're going to have to move away from these fuels as our trim. Instead, we have to move to a coolant. So this means we're going to shift the energy balance of the furnace slightly. So currently these furnaces are designed to be slightly energy negative, and that trim fuel adds enough energy to get it smelting at the temperature we want. If we run at energy positive, rather than using a fuel down the lance, we can use a coolant. So we have tested and done some things here. One thing which we've identified as practical is the use of water. So this might sound surprising, but the intense bath agitation means that we can inject water into the bath without having major issues. And so this has been proven in industrial sites in Africa and other regions where they've had significant water leaks and other things pouring water into the furnace without an explosion. So a number of sites are looking towards this and have approached us to change out their fuel systems to water injection for the trim control. And so that's probably the 3 there. So you can see that there's a few steps there that we're looking at to get us towards net zero, but we're very, very close with the technology as it currently stands. So when we look at what we've done and what we need to do for the next steps, you can see we're extremely energy efficient. So you can see that's an energy balance for old technology, so things like that were installed at southern Peru and Mount Isa, and you can see you need a huge amount of fuel for the energy balance. So you can see the feed, because it's sulfide smelting, copper sulfides provide energy for smelting. They provide about 11 megawatts. But the fuel they need about 16.7 megawatts to balance out the energy, and that huge energy inefficiencies. The ISASMELT technology, by having those changes we've done, we're able to get extremely energy efficient. So energy efficient, we actually have excess energy from the feed. So the sulfide smelting, when we smelt the copper sulfides, generates energy, and we need to add coolants. So this excess energy, in the order of about 7.3 megawatts, actually provides us an opportunity in our primary smelting flow sheet. So what this means is in those primary copper smelting flow sheets with ISASMELT technology, we can start to include other secondary materials. So things that consume energy when smelting. So sludges, slags, recycle things, copper scraps in our furnace. So we can actually smelt primary and secondary without carbon in the ISASMELT technology, balancing off the energy contents in the different feeds. So there's huge opportunities once we start to implement some of these further advanced systems. So what if, unlike copper smelting, there is no energy in the feed? So this is where carbon fuels have traditionally been used. So those feed materials which don't generate heat when we smelt. So traditionally we've used solid carbon fuels. So this is because they're easy to handle with bins and belts. Carbon you can shovel and you can do your things there, it's quite safe. But we need to start to move to some new things. So there's three sorts of things which have been used for energy in smelting. So those primary copper feeds, those sulfide materials, when we smelt them, they generate energy. So this means that we can use sulfide materials for smelting. So some sort of sulfides we can see out there that might be used is things like pyrite. So as we're moving towards zero carbon, we're going to need to use alternative sulfur sources. So a lot of the sulfur we have comes from the oil and gas industry, and people are talking about pyrite needing to be used to generate acid for fertilizer use. So pyrite will be an interesting energy source in the future to sort of use for smelting. There's also some other sorts of materials, such as leach residues from the Albion process, and other sorts of sulfide materials, which we can sort of mix and use, which are very rich in sulfur and can provide an energy. Next one along is your metallic materials. So this is things like shredded steel and aluminium. So this is used for metallothermic reductions. So long term in the future, this is, while possible, probably going to be quite challenging, because when you use those metallothermic materials, aluminium and iron, you convert those metals into oxides. And so you sort of have to have a smelter or a facility to produce metals to then feed your other facility to make other metals. So you sort of have to have lots of facilities and sites. So a bit of a cyclical challenge there. So this one's possible and might be used for some specialist metals, but not likely to be compared to sulfides. And the last one, of course, is hydrogen, which is talked about a lot. So this one here, we've proven that at the crucible scale, and probably more work is going on there, and there's lots of research and development out there in the industry on this topic at the moment. So lastly, maintenance and consumables. So we've talked a lot about scope 1, so that's everything we control within the smelting furnace. Scope 3 is about the things that are used to construct and maintain your smelter. So first of all, when you're looking at construction, so smelters use a lot of materials to build them. You've got buildings, equipment, all your parts and things there. So there's a number of ways we can minimize this in our traditional sort of approach. So like before, we want to go to net zero, we want to first of all reduce and then replace. So when we want to reduce the amount of scope 3 emissions as far as possible, we want to have as little equipment as possible in the flow sheet. So very small numbers of equipment. We want to have them high intensity smelting. We want to have very compact smelter footprints. So surprisingly, when we assess this for the ISASMELT technology, the ISASMELT furnace is a high intensity smelting vessel. The intense bath agitation means we've got very, very small vessels. We've got very, very small layouts. The layouts of ISASMELT buildings are a lot smaller than other technologies out there in industry. And we've got very little equipment in the flow sheet. So when we looked at this, actually ISASMELT technology is one of the lowest scope 3 emissions when you're building a smelter, because it has high intensity vessels, compact footprints. And as well, when we're looking at traditional economics, this actually also lines up with low capital costs. So smelters that have lower capital costs are more likely to have lower scope 3 emissions in the construction. And when we look at the capital cost, again, ISASMELT is currently the lowest, if not one of the lowest technology options available for smelters. So that just means that when you're building your smelter now, you then need to, once we've got it as little materials as required, you just need to procure low carbon materials where possible, things like green steels. So then the other one, of course, is while you're running your smelter, you then have to bring materials in to your smelting process to maintain, repair and fix things. So things like motors and pipes and things like that. So first of all, again, this is about things before, reducing them and then replacing them. So first of all, you want to have as long a life part as possible. So you want it to last as long as it can before you change it out. Then you want to have the amount of materials used, so small parts, small number of equipment, and then simple equipment. So you can see that in our furnace technology. We focus this a lot on our lining systems. So that ISASMELT lining design, we got very long campaigns with a very small number of bricks. And so this means the amount of materials we use is very small on an annualized basis. So we can easily get 5+ year campaigns on primary copper, easily 5-year campaigns on primary lead. And so you can see we use very little materials. And a lot of that is about that temperature control system. On the other one as well is the other common part that we replace is our lance in our ISASMELT furnace. So this is that simple steel pipe with our slag splash. But we've worked a lot on extending the lance lives. So the initial plants probably had 1-2 days lance life before they had to swap them out. By following a rigorous process of maintenance, monitoring, control of our lances and how we run them, we understand how they work. We're getting up to 30 days at some sites. And as well, the lance itself, we've optimized that and took the initial designs and we've simplified that and made that more reliable. So it means we've got smaller numbers of equipment that needs to be changed. So it's typically just a simple steel pipe. The tip that gets replaced, maybe about 1 meter or so of pipe that gets chopped off and welded on. So very, very little parts there. So you can see there that a lot of the traditional things there about maintenance for costs and building, there's a huge overlap between your emissions reduction approaches as well as your traditional economics ones. So the last one is, what about the circular economy? So people are talking about both low emission smelting and the circular economy, but there's a bit of a challenge. So it's not quite yet resolved, but a lot of our circular economy materials contain carbon. So a good example of that is our e-scrap material there. A lot of that contains plastics, which when we smelt it to recover it, generates CO2. So if we look at how we can remove plastics from the feed, there's a lot of work ongoing there. But this is probably one we need to be careful of in the metallurgical industry when we look at the circular economy of ways which we can manage this, reduce the amount of plastics. This will probably be one of the bigger challenges. But realistically, recycling these materials probably is a better net impact than landfilling them. We just need to be careful of what we do there. So there might be some things in the off-gas system with CO2 capture and storage when we're looking at some of these circular economy things there. So what are the conclusions? So as we've sort of discussed, following that traditional optimization approach, ISASMELT has become extremely energy efficient with very low Scope 1 emissions. We've been implementing proven technology, and so you can see with our existing technology, with a few extra steps, we can become net zero in our primary smelting furnace. Lastly, as well, is optimization of maintenance equipment. ISASMELT is very low Scope 3 emissions. This is both through the plant construction as well as the maintenance purposes. So you can see that in the low carbon future, we're very close, and developing this technology further is going to probably be likely to be an easy way to get to net zero with smelting. So thanks for listening. Thanks to the rest of the ISASMELT team. Thank you very much.
So now we'll move on to our Q&A portion of the webinar, and today we're joined with Technology Manager Dr Stanko Nikolic, and again with Senior Metallurgist Dr Stuart Nicol. We have received a fair few questions already, but please feel free to add any more into the chat and we'll address as many as we can. Amazing, so let's get started. I'll begin with this question. It's a nice general one. So Stanko, what is the timeline for transitioning to net zero in the smelting processes? Where do we start? How do we get through that journey to actually achieve net zero?
I think for us, when we look at the majority of our furnaces around the world, the journey for them needs to look at the fuels that they're using in their smelter, what they're looking at doing for their actual carbon journey in terms of understanding where those emissions come from, and then talking to us as a technology provider or some of the other people that we can network them to be able to identify those really quick wins for being able to reduce those emissions. So I think that's really the pathway to get there. We need to identify that, and then we start doing the hard work on getting that last 20% that may need some other kind of carbon offset or capture to be able to actually make that real net zero drive.
Yeah, it sounds like Nicol Technology is so willing for a bit of back and forth to help you understand your flow sheet first and then optimize in the most economically feasible way to achieve that goal. So that sounds amazing. Okay, so next question. This one's for you, Stuart. Is it actually feasible to meet net zero even with carbon in the feed? So whilst we've done all these optimization works, even when there's more carbon coming in through, some sources, what can we do about that?
So this is actually one of the biggest challenges. So both primary and secondary materials contain carbon in them. So the primary materials, that's from ore bodies that contain carbonates, so calcium carbonate, magnesium carbonate, those sorts of materials. And you've also got some native graphite. So some regions in Africa, they've got native graphite in a lot of their concentrates. So when you smelt those two materials, you'll always be producing CO2 unless you've got really advanced beneficiation processes, and they'll never be perfect either. Then when we look at the second one, secondary materials, as we mentioned, that all contains plastics.
And again, separating them out using the beneficiation techniques we have, people haven't found a good way to pull out the carbon effectively. So we'll always be likely putting some carbon into the smelting process just due to the feeds we have. We want to reduce it as far as possible. So if you did want to have a true net zero smelter, it's probably one of the bigger challenges. So you may have to put something like a carbon capture system on the end of your off-gas system if you did want to pull out that last carbon that be there.
Yeah, and that sounds really aligned with what Stanko said around the quick wins first and then what you can do at the very end to really close off that loop. And yeah, it also sounds like obviously Glencore Technology has so much experience across the world. You kind of know how it goes with all these different things and what kind of different ore bodies and mineralogies there are out there. So yeah, amazing. Okay, so the next one. So Stanko, how can Glencore technologies be integrated into existing smelting operations to reduce carbon footprint?
No, that's a great question. I mean, when we look at the majority of the work we've done in the industry, be it copper smelting or lead smelting, even recycling, if you look at some of the plants we have in Europe, it's all been about working with an existing facility or an existing operation, and then being able to look at how do we fit our technology within that site. And therefore, it's all about retrofits, brownfield sort of projects where space is a real big constraint. And that's one of the big advantages we have with ISASMELT, being able to fit those, fit our furnaces within those sites. And so then that way we can actually help our clients make use of the space that they have to be able to actually look at implementing our technology to achieve that. And I think Stuart gave the example of Southern Peru in the actual presentation a little bit earlier, and I think that's a really good one because that was an ISASMELT that was installed in an operating plant. And then we switched across over to the ISASMELT once everything was ready and hot, and we were going to put feed on to that plant.
Amazing. Okay, and with that, when you're going to implement the ISASMELT technology in the flow sheet, are there any big hurdles that impact this adoption that potential clients should consider before making a purchase?
So as I mentioned in the presentation, we've done most of the things. So pneumatic injection systems, high industrial oxygen enrichments, those sorts of things are very well proven in our technology. The biggest one, of course, is hydrogen in the ISASMELT lab. So we did do those tests a number of years ago. We still have to sort of update them and scale them up. So we have got more work going on there. So we're likely to be stepping through our furnaces. So we'll be doing F600 tests, followed by F1100 tests, and then after that, be able to implement that in industrial applications. The valve trains and designs, they're well proven in the gas industry, so people are fairly confident with hydrogen bridgement steels and the valves and systems there. So that's all probably our path there. The other one, of course, is a lot of burners used to heat the furnaces and keep them hot. So there's a few burner vendors and equipment suppliers we're talking to that have got solutions. And so I was talking to one of them a few weeks back, and they were showing me videos of their hydrogen burners, which they were able to install in metallurgical facilities. So there is a path forward. We're fairly confident we can move there, but it's probably the hurdles we have to go through.
Yeah. No, amazing. And I will just touch on the hydrogen kind of aspect again too. I know hydrogen is so important in this broader discussion of decarbonisation, and there is a lot going on in all the other industries to kind of solve those challenges. So collaboration there, sharing knowledge is really helpful, and how we can all leverage each other to figure this out. So could you tell us a little bit more, Stanko or Stuart, about the hydrogen tests that were done previously and what the plans for the future are around hydrogen testing?
So we did some demonstration tests in leaded slag reduction on the 1 kilogram scale back in the late 80s, early 90s. So as we sort of mentioned, we chose not to progress this at the time with the technology just because of the production of hydrogen. The handling of it was more operationally difficult than the use of standard carbons in our smelting process. So we chose not to progress it at the time as a result. So from the test work, we identified and showed in that scale that the hydrogen-based reductant was able to work in the furnace technology. There are some slight changes in the reaction kinetics. So hydrogen generally does reduction faster. So the adsorption, desorption of hydrogen and water in the materials is faster. That speeds up some reaction processes, which is quite nice. But if you look, there's another key difference is it does increase the off-gas volumes. So the amount of off-gas per reductant is roughly double, and that can impact some of the processes. But we do know that work and test work we did, we just need to work through it all.
Yeah, that's so exciting. It's so cool that it's already been done, and yeah, it's just going to be building further on that. Okay, amazing. I'll just go to a few more questions we have rolling through. So you mentioned that industrial oxygen will be required. Are there any CO2 emissions associated with this?
I guess when we look at industrial oxygen, it has been used as a way to intensify the smelting process, if you look back in the past couple of decades. And when we look at those oxygen plants, there's a number of different varieties of technologies out there, cryogenic or also the pressure swing as well. And when we consider, well, what's needed to make that happen, we do need power. There is energy needed to be able to actually produce that oxygen. But really, I guess what we're at is in the transition for the energy area is that we don't have to just rely on fossil fuels for providing the energy for those oxygen plants. So therefore, if we're in a particular jurisdiction where perhaps there's hydroelectricity, then for them, it's actually quite easy to quickly make that transition. They can source that electricity to be able to use that to then generate that oxygen from a net zero perspective. But for other areas, they may have to look at other renewables, be it wind or solar, to be able to actually create that same level of net zero when it comes to producing the oxygen.
Yeah. Amazing. And then a final question before we wrap up today. How will proposed changes impact the smelting process? Is there any issues associated with the products? Or is it just going to be amazing advantage and, still quality products at the end?
So there's probably two things here, which are a bit of a change from our traditional processes. So the first one is if you do start to use some of those alternative materials or fuels, such as pyrites, you do potentially increase the amount of slag you're producing in your smelting process. So if you do increase the amount of slag, that means you have to do more slag handling and slag reprocessing. And you're also likely to slightly decrease metal recoveries, because slag will carry the valuable metals. That's all a trade-off for the economics. The other one that will come into play is some operability changes. So one of the key advantages of ISASMELT technology currently is the flexibility of the smelting process. We currently get about a 1:3 turn down ratio. So some sites can run anywhere from 50 tonne per hour to 180 tonne per hour without any issues or challenges. There's no problems in the smelting process. But when you do go towards higher industrial oxygen enrichment, where you just have pure industrial oxy and you do pneumatic injection, that turn down ratio is a bit more restricted. We still have to do the designs and figure things out with how restricted and what the impacts are. But we will likely reduce some of that turn down ratio on the technology. So there may be having to be some backup systems to improve the flexibility, like maintaining some belt systems and things like that. We still have to go through the design process there. But if you did go all the way, just dry column injection and industrial oxygen, there's a slight decrease in operability.
Okay. Amazing. Good to hear that there's always solutions and there's always a way to kind of optimize the process and figure things out. Again, with Stanko Technology's experience across, the whole industry and so many insights from that, there's always a way to solve these challenges and have amazing products at the end. Okay, well, thank you so much, Stanko and Stuart. We will wrap up the Q&A portion now, but if you do have any other questions, please feel free to continue sending them in and we'll get in touch with you. Thank you to all that were able to attend this live webinar and those viewing the recording. We hope you found this session of value and will join us again for more sessions in the future to discuss Nicol Technology's sustainable flow sheet options. For further information on net zero smelting, please don't hesitate to reach out to our friendly team through our website. Technical papers, equipment details and installation information are also found on our website. The time is now for base metals producers to upgrade their smelting flow sheets and decarbonise with ISASMELT. Thank you once again, and we'll talk with you shortly.